Hello, my name is Rohan Dominguez, and this is my Triple E 120 Lab 1. So first we have our half adder, and the half adder is just a logic setup that doesn't take any carry in, but accounts for carry out. So as you can see, we have a XOR gate, and we have an AND gate down here. We have a sum and carry outputs, and an A and B input. So we can just test how it works. So if A is 1, that meets the XOR gate requirements, and that'll have a sum of 1. Same thing if just B is 1, that meets the requirements of an XOR gate since a even or an odd number of inputs needs to be 1 for an XOR gate to output a 1. So we can see sum is 1 when just A or just B is 1. If neither of them, obviously we can see sum is 0 and carry is 0. But if are both are 1, you can see our sum is again 0, however we have a carry. Carry is an AND gate, and it requires both A and B in order to have carry. So we can see this setup in GTK wave. Is our half adder with A up here, B carry, and sum. So for example, A and B are 0, our carry and our sum will be 0. If A is 0 and B is 1, or if A is 1 and B is 0, both these have a sum of 1 and a carry of 0. And carry is only 1 when A is 1, B is 1, and then our carry will be 1, but then our sum will also be 0. So that just matches what we had in our digital file. So with comparing it to the text file, we can also see that um, with left being the output and right being the input, this matches what we had said earlier. So here we have a logic setup with 4 half adders and an incrementer. So we have an input A. We have an incrementer over here. 1, 2, 3, 4 half adders with each A and B and then a sum and carry. And then we have our Y output and our carry. So we can just do some tests like, for example, A is 0, our output will be 0. If A is 2, our output would be 2. And if we increment that, that would mean our output is 3. So our incrementer would be 1 more than our input, which would make our output 1 more than the input. So, and then we can test for carry out. Carry out, since it's in hexadecimal, we should have carry out when our input A is F, or 15 in hexadecimal. And then we have an increment of 1. So that should be our case where we have our only case where we have carry out in this. So if we were to take the increment out, our sum would be F, which is our input, no carry. Increment, we would have carry, and our input or output value Y would go back to 0. And each of these nodes right here in our splitter represent one of the bits in the hexadecimal. So this is bit 0 and bit 1. So as you can see, 2 plus 1 is 3, and our value is 3. So you can just see how this matches. This is our second bit, and this is our third bit. Same thing out here, but this just goes to the output. Since this is our let's see. We're to make our output 5. As you can see, this bit would be 2, which represents 4. This bit will be 1, or this bit would be 1, which represents 1. So 4 plus 1 is 5. And then here's our GTK wave. As you can see, this GTK wave goes exactly with how our digital file went. So, for example, if A is 1 and our increment is 1, right here, that'll be 1 plus 1 is 2. 2 plus 1 is 3, etc. And then here, when our increment is 0, and input's 1, so 1 plus 0 is 1, 2 plus 0 is 1. So as you can see, this goes for all the cases where the increment is 1, and then it shows you what happens when the increment is 0, that our input A would be exactly the same as our output Y. But when the increment is 1, our output Y would be 1 more than our input A. Here we have our full add logic system. We have input A, input B, carry in input. We have a sum, and we have a carry out. There's 1, 2, 3 AND gates, an XOR gate, an OR gate, and these are our outputs, and all the wires connecting all the things. So again, our inputs are 4 bits, and our outputs are 4 bits. However, we're just going to use the rightmost 2 bits for our output. So that would be carry out and sum in that order. And then we'd use the 3 rightmost bits for our inputs of A, B, and carry in that order. So we can do some tests. So if A is 1, that would mean there's a 4. So we can check 4. Let me say that the right side is our the right is the input and the left is the output. So right side will have 1, 0, 0, which is 4. So we can look at 4 on the right. And then carry is 0, sum is 1, so that's 0, 1, which is 1. As you can see, that test case works, so we can do another one. We can make B 1, that would be 6. And then, because that's 0, 1, 1, or 1, 1, 1, 0, so 4 plus 2 is 6. And then we have a carry out of 1, sum of 0, so it would be 1, 0, which is 2. So we should have a 2 on the left, 6 on the right. And then, yep, that's one of our test case. So we can see this program is working. And we can go into the GTK wave of this. A on the top, B, carry in, carry out, sum. You see A is 0, B is 0, carry in 0, carry out 0, sum 0. Well, if we have A 0, B 0, carry in 1, that's 1. So our sum would also be 1, and we have no carry out. We could also test it logically without using any bits. So we can just see that an XOR gate needs an odd number of inputs to be 1. So we can just see having 1, make the sum 1. Just B, same results. Just carry in, same results. If we have 2, none of the combinations will work. However, the carry out will, since there's an AND gate, this AND gate specifically, and then that goes to an OR gate, and then carry out. But if we have all 3, the OR gate, the XOR gate works again, and the sum is there. And then all these AND gates are returned to true. This OR gate turns true, and then carry out. So this is our situation where we have a sum and carry out. Sum is 1 and carry out is 1. Final is a 4-bit adder. So we have input A, input B, carry in. 1, 2, 3, 4 full adders with each an A, B, carry in input, and a sum and carry out output, leading to an OR gate or XOR gate with overflow, carry out, and Y being our outputs. So all of these represent digits in hex. So as you can see in our text test document, there's 5 hexadecimals. Column 1 is the expected values for overflow and carry out in that order using the right 2 bits only. Um, column 1 is the expected sum. Column 2 is our carry-in value, either it could be 1 or 0. Column 3 is our A input. And in that one, we're going to be using, well, carry-in, we're only going to be using the right bit. A and B, we're going to use all 4 bits. Yeah, so column 4 is a B input, column 3 is A input. As you can see, we can mess with this program to change different things. Our output Y would increase. So we're going to run through some test cases. So we're going to have B be 8 in hexadecimal. We're going to have A be F or 15. And then our carry-in will be 0. So with this setup, we have a output of 7, overflow of 1, carry out of 1. So let's see how that is calculated. So as you can see, B is 8, A is F, carry in 0. So carry in means we're just going to have zeros at this rightmost bit at the top. This is our F, 15, 1, 1, 1, 1. 8 is going to be 1, 0, 0, 0. So as you can see, 1 plus 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry, which is 0, carry of 1. And since these two don't match, we're also going to have overflow. And then if we have a carry and overflow, that's going to be 1 plus 1, which is 3. So that's how we have 3. And 0, 1, 1, 1 is 7. So that matches our 7. Our other test case is going to be 2 for B, 6 for A. 1 carry in. So we have carry in here. 1 plus 0 is 1. 1 plus 1 is 0. Carry 1. 1 plus 1 is 0. Carry 1. 1 plus 0 is 1. So as you can see, our 1, 0, 0 is our expected output of 9. And we have no carry out. However, we do have overflow since these two do not match. And overflow, no carry out would just be 1, 0, which is 2. As you can see, that matches. And here's our GTK wave of this simulation. As you can see, it matches some of those test case situations that we tried. A is 3, B is 3, our sum, or Y would be 6, 2, 2, 4, 1, 1, 2, etc., etc. Thank you for watching.